Welcome to lecture 6. Today we study GPT. Okay, so before the lecture, did you watch these videos this week? Yeah, it's made by Sora AI model. Yeah. By the way, do you like the video? Do you think the videos are good? By the way, do you think it's a cherry pick results? Have you tried the Sora? Yeah, we don't know, right? Maybe they are cherry pick results because I tried something like DALL-E 2 for the AI painting. Sometimes it's very bad. I think generating videos is even more challenging than pictures. So I suspect maybe some of them are cherry pick results. Yeah. So any comments you have on Sora?
Even if it's cherry picked, it's still very impressive.
Yes. Yeah. But at least we know a lot of work we can do in the future. I think this kind of product or research has a lot of space in the future. Everything can be video, right? You play games, you watch TV, or even for your study, you want to have a better understanding of the knowledge, you can just share the video. Yeah, so I think that's very revolutionary. It's very important for the future. All right, let's just watch 3 minute video before class.
Drone shot. The kind of video that you might see in a travel video, right? Except it's not real. There is no drone. There is no camera. You can't travel because the video was generated by AI. It's from a new tool just announced a few hours ago by OpenAI called Sora. All it takes is typing in a short text, a prompt, and in minutes it spits out a 60-second video clip of pretty much anything you can imagine. Brian Chung is here to break this all down for us. This is cool, Brian. I mean, yeah, it could mean millions of people, though, could be out of work, right? Because who developed this video and what kind of an impact might it have on the jobs market?
Yeah, it's really mind-blowing. Some other video that we saw was of a woolly mammoth in a tundra. We also saw a little monster lighting up a candle, and none of it was done by any animators. All you have to do is enter in a text prompt. You hit generate, and it creates what you see in front of you. Again, nothing was shot in this case. It's all AI generated. And obviously, this is a concern in Hollywood, where you have animators, illustrators, visual effects workers who are wondering, how is this going to affect my job? And we have estimates from trade organizations and unions that have tried to project the impact of AI. 21% of US film, TV, and animation jobs predicted to be partially or wholly replaced by generative AI by just 2026, Tom. So this is already happening. And I have to also point out this tech is from the makers of ChatGPT, so very much a big technological jump for that company.
Yeah, but scary. I mean, Brian, what if I typed in right now, I want Brian Chung to tell me about the stock markets, and then I want him to walk down the street and buy a Starbucks?
You wouldn't even do that. It might, and you wouldn't need to do it. But here's the thing: there are some things inside the announcement today that came from OpenAI with regards to the way they would protect you, for example, using my likeness. So user policies that they already have in place, the company says, will reject violent or hateful images, sexual content, celebrity likenesses, IP of others. They also say that they're engaging policymakers, educators, and artists as they develop and test this technology, which, by the way, OpenAI tells me they don't plan on releasing to the public anytime soon. But regardless, even if they say that, what we see is that in practice, it's hard to stop. The issues with the deepfake portal, for example, with Taylor Swift's likeness, just illustrates how difficult it is to police these things. With video, it's very much an issue.
Yeah, and you got to worry about the impact on elections. We're always seeing AI used in fake election campaigns. You got to worry if it's going to get this sophisticated. You can't tell the difference. Where is this headed? I got 10 seconds for you.
Yeah, and that's the thing where they're trying to consult again, policymakers, industry groups, but what that yields in the long run, it remains to be seen. Again, not yet released to the public, but at some point it very much could be very prevalent in the entertainment industry and beyond, Tom.
Thanks for watching. Stay updated about breaking news and top stories on the NBC
Okay, good. That's a video. Yeah. So now let's go to today's lecture. We start a GPT for today. So before the technical part, let me introduce an interesting blog post in 2020. If you like, you can Google this blog post. Feeling unproductive. Maybe you should stop overthinking. That's a very good blog post. Actually, so it was ranked as #1 hacker news. Yeah. So if you like upper class, you can check this blog post. Very, very interesting. So now the question is, so why this blog post is related to today's lecture? Because this blog post was actually created by GPT-3. Okay. It was not created by human being. It's like a movie wins the award. It was created by AI. Okay. Yeah. And the MIT Tech News actually is a very high standard tech media. So they reported this blog post. It was so amazing. So AI had cheated a human being. So we cannot. So you see here, even on Hacker News, I think the community members of Hacker News are very serious. There are some of them they like tech news. They are developers. So the audience are so good and they cannot tell the difference. That means the AI model is so powerful. They can cheat a human being. Okay, that's the beginning of GPT-3. So let me also give you a brief history of the GPT model. So in June of 2017, a paper, the paper of Transformer was proposed, published by Google. Transformer, the model has roughly 200 million parameters. It's actually a very large model in 2017. So by the way, this month, the GTC conference, NVIDIA CEO Jensen Huang will have an interview with all the authors of the Transformer. If you like, you can check the GTC conference sometime this month. GTC is very important AI tech conference for now. Okay. So that's why this paper is so important. And in 2018, in June 2018, so GPT-1 was published. So GPT-1 actually only has 120 million parameters. GPT-1, I think, was a small success compared to GPT-3 and ChatGPT. It's just like a good tech paper, a good research paper. And the same year, October of 2018, BERT was published by Google. So BERT was a larger model with roughly 315 million parameters. So I think BERT was a very big success. So I think in 2018, so most of the people they use BERT. I think between 2018 and 2020. So BERT was a big success, especially in the AI community. And then later, February of 2019, GPT-2 was published. GPT-2 had 1.5 billion parameters. And then GPT-3 in May of 2020. GPT-3 is a huge model, 175 billion parameters. So you see, GPT-3 was published roughly 4 years ago. However, I think even for today, it's still very challenging for us to run GPT-3. I feel like you can try after this. It's almost impossible on your laptop. The model is so large, 175 billion parameters, right? It's published 4 years ago, but even for today, it's still, I mean, the normal researchers, students, we still cannot use GPT-3 very easily. So, which means we still, there's still a lot of work to do to make it more useful and more accessible. So now, for the first part of today's lecture, let me introduce GPT-1. Okay, you see, that's the paper published in 2018. Okay, so the title of the paper is interesting: improving language understanding by generative retraining. So I think the GPT model is sort of generative pre-training transformer. Okay. This reward is also GPT. Okay. So there's a superstar in the AI community. The first author of GPT-1. It's very interesting. This person was also the author of DC Gun, GPU reinforcement learning, and many famous work. It's just like the Tom Cruise in for AI. And this is like the godfather for large AI models. It's like the Michael Jordan for LLM. So Ilya was the team leader for GPT-1 paper. Also, he is the chief scientist of OpenAI. Also, he is the author of AlexNet. That's the starting point for the AI wave. Very, very good team. Okay, now let me give you an overview for GPT-1. So the idea of GPT-1 actually is very useful. It's just a combination of unsupervised pre-training and supervised fine-tuning of SFT. So even for today, SFT is very useful. So why this is important? Because we know training AI is very expensive, right? As I mentioned, so GPT-3 was proposed in 2020. Even for today, we cannot train it on your laptop. So because it's so expensive, so we wanted to train the model just once, and then we use the pre-trained model on 100 applications or 1,000 applications. We just want to train it once. We don't want to change the model. We want to we don't change the model architecture, and we reuse it for 1 year or 2 years for 100 different situations. Okay. That's why it's so interesting and important. So we want to minimize the cost. Also, GPT-1 achieved very good results. So actually, they won 9 of the 12 benchmarks, which was very impressive. So here is just a brief overview for GPT-1. Firstly, we have a large data set like Wiki. We pre-train the model, and then we use a small data set, but this is actually a high quality data set. this we may need to label this data set. This data set is a high quality data set, but it's much smaller. So we use this data set to fine-tune the model. After model is fine-tuned, we use a model for our real-world application. That's the basic overview for GPT-1. So now let me give you some background information of GPT-1. So why do we need a GPT-1? So why GPT-1 is necessary? So the background is, so we don't have enough labeled data to train language model. So we know before GPT or before transformer, the most popular AI application are computer vision application like face recognition, like image segmentation. So this kind of model often they have the training data set like ImageNet. So ImageNet I think has roughly 13 million or 14 million images. Even a small version of ImageNet, you can just use 1.3 million images. So for computer vision applications, we have a lot of high quality labeled data. So that's why we can train very good model. But for here, for language model, it's actually very challenging. So why is it challenging? So here is a quote. I hope you heard this quote before. So a picture is worse than a sound worse. So that means now, if you have one image, if you want to train the same number of meters for both computer vision and the language, you need 1,000 words. That means for regular model, maybe you need 1 million images to train the CB models. Now you need 1 billion words or 100 million sentences to train the model, to train a small model. We need so much data. That's very challenging. And that's not easy. So by the way, for this kind of data, like 1 million image, you just need to, you can only train the model like Resident 50, which only has 25 million parameters. 25 million parameters is very good, is a very small model, right? GPT-3 has 175 billion, roughly 10,000 times larger. Now, 10,000 times larger. So you see, you need a 10 trillion, 10 T words, roughly 1 trillion sentences. That's very challenging. So that's why we need to learn the useful information to train the model by the unlabeled data, because we just cannot build enough labeled data. That's why we need a GPT-1. Okay, by the way, any questions so far? Okay, good. Yeah. So now, after we decided to use the unlabeled data, the second question is, how can we use unlabeled data? Is it easy? How can we train the model with unlabeled data? Actually, it's not easy. Why it's not easy? You see, so here is here is a visualization for different language application, right? We have so many different NLP applications. So different applications, they may need different training objectives. So how can we build the universal? How can I build just one objective function or just one model can work for all the applications? That's very challenging because different applications, they are so different from each other, right? For example, the sentimental analysis is very different from machine translation. And now we may have 20 different NLP tasks. So we just don't know what kind of objective function or what kind of the model we can use. And even the model was trained, even we can get an objective function. So for fine tuning, and it's also very challenging to transfer the knowledge from the pre-trained model to the fine tuned model. So because we just want to train the model once, we cannot, because for here, assume we have 100 applications. We just train the model once, we cannot train the model 100 times because that's too expensive. So how can we train the model once and then transfer the knowledge 99 times? That's the challenge for using unlabeled data. Yeah. So now that's why the author proposed GPT-1. So GPT-1, when GPT-1 was proposed, according to the author, it's a semi-supervised learning or semi-supervised training. So why it's semi-supervised? Because it's a combination of first stage and supervised, second stage is supervised. Because first stage we just get the data from the internet, like a wiki. And the second stage we just hire 100 college students to label the data for us. It's supervised. It's supervised learning. Okay, so why the author claim that it's semi-supervised, but actually it's just some different terms. So today we just call it self-supervised learning. So now for this, we wanted to learn universal representation, and later we wanted to transfer the knowledge to 1,000 applications or 10,000 different applications. Yeah. So here, just the two stages I mentioned for first stage and second stage. Now, let me give you more information about the model. I think in the future you may know you may need to learn many different kinds of AI applications. I think no matter how complicated is the application, you need to know the model structure and also the objective function. For any AI models, please make sure you understand the model structure, the model architecture, and the objective function. So firstly, let me introduce the model structure. So they use transformer. So here is the visualization for the GPT structure. Firstly, the input, and then we have the embedding. That's the positional coding, actually here is just processing the data, and then the dropout is commonly used trick. And then is the GPT block is a key part of the model. So here is a visualization of this block. And after GPT block, like L blocks, like L can be 12, can be 20, can be 30, can be 100. We just repeat the same block many times. And then the layer norm, and then the fully connect layer. And then we use Somax to compute the probability. Right. So the most important thing here is the GPT block. Let me Let me give you some brief information. So by the end of this lecture, I give you more detailed information of how can we compute this. So in this GPT block, you see it's very interesting. So firstly, layer normalization. Now let me ask you a question. So assume this layer. Let's assume the input of this layer is 10 billion by 2 million. Let's just assume this layer, the input shape is a matrix 10 billion by 2 million. So what's the shape of output? So the input is 10 billion by 2 million. What's the output shape? Anyone has an idea?
One times
No. Yeah, it's actually the same. It's also the 10 billion by 2 million. It's elements element-wise operation. Please make sure you understand the layer now. It's element-wise. Output and input has the same dimension. And then is our multi-head attention. I hope you remember we introduced multi-head attention before, and then drop out. And then it's still there now, and then fully connect and drop out. That's the structure for GPT-1. So for GPT-1, L here is 12. GPT-1 has 12 layers. Yeah. So here the first question is why we use transformer? Why don't we just use RNN? Because in 2018, when this work was published in 2018, RNN was still very popular. Today, no, I know no one uses RNN. In 2018, I believe RNN was still very popular. LSTM, right? So why we use transformer? Yeah. So here probably this is from the paper. So they claim because can be better for the structure memory and handling long dependency, and also more robust. You can see it's more like empirical study. So the author just found it's easy to use transformer, easy to scale. So maybe in the future, maybe 5 years later or 10 years later, some researchers maybe probably find a good way to use iron. Iron can also become more popular. So that's just empirical study. And another important thing, another important advantage of transformer is parallel computing. As I mentioned, we can compute different tokens in parallel, right? In parallel. For iron, it's like a serial computing. It's not friendly for GPU. By the way, now the market value for NVIDIA is over $2 trillion US dollars. You see, in the last few years, so many, I think so many applications running on GPU, 99% of them are transformers. That's why GDC conference, Jinzhen Huang wants to have interview with transformer authors. They make NVIDIA successful. Yeah, I feel like you can check the interview between the transformer authors and Jinzhen Huang. Okay. And the second question is why don't we use encoder? So why decoder? So encoder is also very good. So why not the encoder? So here, I think that makes sense. Actually, later I will introduce because the objective function of GPT is to predict the next token. Decoder is very suitable for this. So because GPT has a very special objective function, and the decoder is probably the best building block for this training objective. That's why they choose decoder, not encoder. Now, let's take a look at the objective function for GPT. So you see now, the U here is the data. So it's probably just like maybe 100 or 200 tokens from a wiki article. So we use the tokens, hundreds or thousands or even millions of tokens to the model, but for each step, we just get some tokens. How about we just get k tokens? Because we have very limited computing power, we cannot put all the tokens, put all the words. We cannot put 10 billion words to GPU each steps. So here, for example, k is 100 or k 200. That's each iteration. We just each step we just get 100 tokens. So we predict next token. Okay. You give me 100 tokens. I predict the next word you want to say. That's just the idea of GPT. So you see, so here is the background information. Theta here is our model. UI is our prediction. We just keep predicting the next word. That's the objective function for GPT, right? It's actually very easy. Just predicting the next token, next word. And then we want to maximize this probability. You see, we do not need to label any data, right? Because in the training, we know what's the next word. We know. Okay. Any questions so far? Okay, good. Yeah. And how about after pre-tuning, we do the supervised fine-tuning. So for supervised fine-tuning, now we have some labeled data. We have some labeled data, that's good. We just use the labeled data to build a loss function, right? So like that's a sentence, that's a sequence, and that's a label. We just maximize this, the prediction in this label, maximize the probability, just like the common case, a common machine learning task. We can also put them together to build a new loss function. So here, lambda here just have. So you see today, ChatGPT is so powerful, but the training objective function of GPT is so simple. Right? You just predict the next word. Now, after the model is trained, we want to transfer the knowledge to different applications. So here, the author gave us some example, right? So assume this guy, this part is a model, is a pre-trained model. Now we just change the last layer or something to just change it here. You see, we can fix the model just to change the last layer to build a new task. Right? But as I mentioned, you can also fine-tune like classification, entailment, similarity, multi-choice. Here you can see, so for classification, often you have a sequence or sentence. You want to predict this sentence is positive or negative. For example, I hate Michael Jordan, maybe it's negative. Right? I love Kobe Bryant, maybe it's positive. Right? So like entailment. Firstly is premise and the hypothesis. So for example, Tom gave Jennifer a flower, and the hypothesis Tom loves Jennifer. It's just a simple example. And also we want to know the similarity between the first sentence and second sentence. That's the multi-choice. We have the same question, different answers, right? We may pick one answer or two answers. That's just for different application. Okay, let me also introduce the experimental details. Firstly is the training data set. So they just use 7,000 unpublished books as the training data set. So by the way, do you know how many words in a book? How many words in the book, or how many tokens in the book? Anyone want to have a guess?
The 20,000.
20,000 in a book, right? Okay, okay, good. 20,000. Now we have roughly 100 million. 100 million tokens, right? Because we have 7,000 books. So now the model, as I mentioned, has 12 layers. So the hidden size or the model size is roughly 800. So they also have 12 attention height. So total number of parameters is 125. Okay. Yeah, it's still a small model compared to GPT-3. So here, let me show you some results. So when this paper was published, they actually achieved the very good results. So this paper was the first column. These models are state-of-art methods in 2018 on different benchmarks. You see, that's GPT-1. GPT-1 win 4 of 5, or 4 out of 5. It's very amazing. And so here is on some QA and reasoning tasks. So GPT win all of that. Yeah. So by the way, I want to ask the TA. So these benchmarks, are they still very important today? Because this paper was published in 2018. Are they still important today?
I don't think they are still widely used today because we use more famous benchmarks like super glue lines.
Okay, yeah. So these results in 2018, right? Today we have new benchmarks. But at least they can in 2018 they are very important. So again, GPT wins 3 out of 5 benchmarks. Okay, now let me give you a comparison between GPT-1 and BERT. So I think in 2018, both GPT-1 and BERT were published, but BERT became more famous and also more popular. I think today is 2018, so GPT-1 and BERT are two most important models. So what's the difference between GPT-1 and BERT? Firstly, they kind of use the same strategy, pre-training and fine-tuning. And but they use different objective function. So that objective function for GPT-1 is just predicting the next word, So that's the objective function for BERT. We wanted to predict the masked token. Like we have a sentence, we remove this part, we make a prediction for this word of this token. So you see here, so GPT-1 is more like predicting the future. BERT is like bridging the gap. Do you think which one is more interesting? Predicting the future or bridging the gap, which is more interesting? But at least predicting the future is more challenging. That's why probably GPT can be more powerful. Okay. Let me also give you a comparison for the architecture. As I mentioned, the GPT is a decoder architecture, BERT is encoder. So that's the hyperparameter for GPT-1, and that's the BERT. That's the 12-layer BERT. That's 24-layer BERT. So you see that that's a configuration, like you can check. So again, in 2018, BERT was more successful. BERT was more successful than GPT. Yeah. So here is a comparison between BERT and GPT-1. I think BERT will win all of them. BERT will win all of them. So that's why people loved BERT so much in 2018. But if you check the history, you can see GPT-1 actually has a higher level of innovation than BERT. GPT-1 proposed this strategy, the pre-training and fine-tuning. That was proposed by GPT-1, not BERT. So that's why GPT-1 actually has a higher level of innovation. So also, as we know, the following years, now GPT is a winner today. So after GPT-1, now let's introduce GPT-2. Again, it's also from a research paper. So the title is language models unsupervised multitask learners. That's GPT-2. So let me give you an overview for GPT-2. So what's the difference between GPT-2 and GPT-1? Firstly, they use larger data set. Now they use information from internet, millions of web pages, and they make the model larger. Now the model has 1.5 billion parameters, 10 times larger than GPT-1, 5 times larger than BERT. And now they claim that they use zero-shot learning. What's the idea of zero-shot learning? Let me explain later, but here the idea is no more fine-tuning. No more fine-tuning. Even we do not fine-tune the model, we can still get good results. We just train it once and use it. No more fine-tuning. That's zero-shot. So maybe the question here is, why do we need a GPT-2? Because we already have GPT-1, why do we need a GPT-2? The first reason is GPT-1 lost the game, right? Because BERT beats GPT-1. They want to win the game again. So they believe GPT needs to be improved. So how can we improve GPT? Just make a larger data set, larger models. So the paper of transformer is attention is all you need. Probably, I think for OpenAI, should be scaling is all you need. Just scale the model, you can get better results. And also, so even for BERT, so it's still not very efficient. Why it's not efficient? Because for each task, it's still we need a specific data set to fine-tune each task. So it's kind of like generalization. It's still not very efficient. The author of GPT, they want to achieve AGI, right? So they believe we should have a very general learning strategy, not something like this. That's why they want to build a GPT-2. Okay, now let me give you a summary for the difference between GPT-1 and GPT-2. Firstly, both of them they have the same objective function, unsupervised pre-training. So the fine-tuning is different. So as I mentioned, for GPT-1, we have to build a different labeled data set for each task. But for GPT-2, they claim that it's zero shot, no more fine-tuning. We just train the model and use it. It's more, I think a step closer to AGI. That's the difference between GPT-1 and GPT-2. Okay, so now let me give you some example of what's a zero shot. So for here, zero shot means we just give the model instruction by natural language. The instruction to the model is just natural language. Like French to English translation, we just that instruction translated to French, and we give the data, the testing data, and then we want to get what we want. And also the reading comprehension, we just the instruction here just answers the question. We tell the report to answer the question, and then we give some information on the question, and then we want the answer. Today it's just prompt, okay? The way we use ChatGPT. So here is a demo, if you like, and you can try it. Okay? Yeah. For example, I gave instruction to ChatGPT to translate to Chinese, and GPT just do it. Right? And also I want ChatGPT to answer the question. I said that the room A has 10 models. Tom gets into room A and killed one model. How many models? It's just that's the idea of zero shot. We train the model, we just use a model. Okay, good. Yeah. So now so here the question is, so why zero shot works? So why it's efficient? OpenAI claimed that it's AGI, but actually it's probably not, because the training data set is so large. They probably have a similar pattern in the training data set. Right? It's probably not a generalization. It's just they learned some similar example in the training data set. Right? You see often in some web page, because internet has everything. Right? On internet, we can get this kind of instruction translated from English to French. Right? We have this kind of instruction on the internet. So I believe, I think when this paper was published, they claimed it's AGI, it's sort of zero shot, but actually it's not. So actually, even for today, we cannot confirm ChatGPT is zero shot or not. Even for today, we cannot confirm because their data just has all the information. They can learn the similar pattern on internet. So now is the setup for GPT-2. So first is training data, right, from Reddit. By the way, you know Reddit is going to IPO recently. It's very success page, right? So they get some web information from Reddit. In total 45 million links or 45 million web pages, 8 million documents. So in total, it's 40 GB text, lots of data. So that's why they can learn almost all the patterns on the internet. Probably a minor question here is, so why they choose Reddit? Do you know why they choose Reddit?
Because the data is not moderated, so you can find all kind of data over there. So maximum range would be covered.
Okay, yeah, very good answer. Thank you. Also, so here is a model information. See different version of models with different number of parameters, with different number of layers, different dimension. So again, for the empirical results, GPT-2 is very good. They outperform all the other zero-shot models. But again, they are not zero shot. I don't believe they are zero shot. They just learn the pattern of the data. So here they also show us some results. Here horizontal axis is a model skill. Vertical axis is F1 score, rule score, some different accuracy. Higher is better. Right? You see here, they skill the model, they make the model larger to get better results. That's the most important thing. That's the most important thing, which means the training strategy is very effective. Now we just need to skill the model, skill the data set. We can always get better results. That's what we want. That means we can control the future. So we just can give the model more parameters and more data to give us better results. That's what we want, very important. So even they do not get the best accuracy, but they are still going up, right? They are still growing. That's most important thing. Eventually, they can win. Okay, now let's go to the number 3 part of today's lecture, GPT-3. So the first version of ChatGPT was based on GPT-3. Also, let me give you an overview for GPT-3. Again, GPT-3 was a huge model with 175 billion parameters. Even for today, it's still challenging for us to train. I hope after 3 years, a graduate student can train it maybe in a few hours, hopefully. And GPT-3 now they don't claim 0 shot. Now they claim few shot. Let me introduce few shot later. So still the idea is no more fine tuning. We just train the model, use it for all the applications. Few shot. And as I introduced in the beginning of the lecture, they can generate something very real, right? The article ranked #1 on Hacker News. Right? They can cheat human beings. That's amazing. So now let me give you some background information. So why do we need GPT-3? So is GPT-2 not good enough? So again, I think probably the same issue. These authors, they just want to achieve AGI. So I think now they also found that so GPT-2 doesn't have the 0 shot ability. GPT-2 just learned some patterns on the training data set. So very easily they have the problem of the data leakage because they can't get the same pattern on the training data. It's just regular machine learning, it's not AGI. And also, they found that for human beings, we do not need to learn many supervised data sets. Sometimes we probably never know the label. We can just learn a new language very quickly. I think a human has the ability of generalization. That's why the author want to propose GPT-3. Just give you a summary. They want to make the model more AGI, make the model better. So here, let me give you the idea of a few shots. So as I mentioned today, ChatGPT, we can use the zero shot. Right? I can just give the instruction, get what I want. And the one shot is when I first give the instruction and then give an example to the model. I translate English to French and then I give the model example. And now few shot, I give the model many examples. Translate the English to French and gives more some examples and more do the translation. I think that's a kind of trade-off because they cannot claim the zero shot because actually it's just learn the pattern from data set. So maybe in next 3 years or 5 years, it's still very challenging to do that. So that's why how about we do few shot. Just like human learn new things, we need to just give humans some examples. They can find the pattern here. That's few shot. few shot is a key part of GPT-3. Okay. Yeah. So why few shot is unique? Because we cannot guarantee zero shot exists in GPT-2. Right? We cannot guarantee GPT-2 has few shot ability. Sorry, zero shot ability. Right? Because that's too fancy, too challenging. Now, probably few shot is something we can rely on, something we can trust. So we use few shot. Okay. So here is a summary. So few shot actually aligns more closely to the concept of in-context learning. Give the model some examples, the model can learn the patterns. That's in-context learning. So we hope the model just learn new things, just like human beings learn by examples. Okay, so here is GPT-3 architecture. You see, we have many different versions of GPT-3. That's the number of parameters, that's the number of layers, that's the dimension of the model, the number of heads, that's the dimension of a head, the base size. So here the base size is actually a little confusing. It's not the number of samples, it's the number of tokens. A little different from the VIT, Viewing Transformer. Viewing Transformer base size is the number of images, right? So we partition each image into different patch. A patch is a token. So often a sequence has a sequence length. So here is a base size multiplied by sequence length in the real base size. Maybe we have 1K. We have 1K sequences. We have 1K sentence, and each sentence has 500 tokens. So it's 500K tokens. That's the idea base size here, and that's the learning rate. Want to ask you a question. So no answer for this question. So when you train your AI models, so what's the learning rate do you use? When you train your AI models, what's the learning rate do you use? No correct answer here. Yeah, for you, you can just just share your hyperparameter if you like.
For me, it's maybe 10 to minus 4.
10 to minus 4.
Yeah.
10 to the power of minus 4, right?
Okay, 10 to minus 3.
10 to the power of minus 3. Okay. Anyone want to share? Okay, so each I want to ask a question. So why the learning rate is so tiny? Because we know SGG, SGG is stochastic gradient center. The learning rate sometimes just 0.1 or 0.5. So today, why we use so tiny learning rate?
From my personal view, one thing is my batch size is too small.
Base size too small?
Yeah, that's specifically for me.
Okay. Yeah, the TA. No, so why today we use so tiny learning rate?
I do not have very theoretical
Okay, because you believe just empirical study?
yeah. Mainly follow the like SOTA work.
Okay.
I guess because our model is too large and sometimes the loss level has a rocket at some point to broke the whole process. So to provide this situation, we need to use very low rate.
Okay, good. Yeah. Please.
I believe it is about the curve. So we want to go into the global minima. So the narrow the curve is, we need to go for small steps. And if the curve is broader, we can take big steps. So because of the limitation of weights range, its weights goes into cost. So weights are wide range, so we can have bigger 0.1 or 0.01. But as the range is very small, we use smaller models. That's why we use smaller alpha.
Okay, good. Yeah. So actually, as mentioned, so we don't know what's the real reason, right? But I think you said it just makes sense to me. Good answer. Yeah. Yeah. I think for this kind of topic, you feel free to share your opinion. Right? Because it's a non-convex normalization, we don't know what's the real answer. Okay, yeah. So, but click into here, you see they use very tiny language, right? Even so, the model is so large. Actually, I think the base size is not. Okay. So here is the training data set for GPT-3. So they use 5 different data sets. All of them are very large, right? So the data set is internet, which has 400 billion tokens. That's crazy. 400 billion tokens. So here, that's a hyperparameter they want to, that's a hyperparameter they want to control. Which data set should I use more frequently? Right. So I have my data set, but maybe some data sets are very important. Some data sets are not very important. Which one should I use more frequently? From here, this data set wiki, to the author, wiki is the most reliable data set, most important data set, because they use wiki 3.4 epochs, more than 3 times, which means they trust the wiki. I think that makes sense to me, because I want to check some facts. I also check wiki. How about you? So not all the data sets are equal. Right? You need to know which data set is more important. Which data set we should show trust. So the first data set, that's just the internet, right? Internet has many random information, right? Maybe has some wrong information. So we just use 0.4 epoch. So even the data set is very large, right? It only accounts for 60% of the training data we use. And also they want to, again, they still want to improve the data quality. They want to use high quality data to check. And then they also want to do some duplication to use their own algorithm to make the data better. And they also add and mix some high quality reference data. So data is very important because they just scale the model. So by the way, if you like, you can check a very successful AI startup in US, Skill AI, SCALE, Skill Space AI. Skill AI is a unicorn in US. They just make clean data for their customers. They make lots of money. So because data today is so important for. Okay, so here is a power law. Let me explain this figure. So the horizontal axis is a compute cost. The vertical axis is the validation loss. The generalization loss. Lower is better. So here, different color means different number of meters. So you see that's a very large model. That's a tiny model. You see after some training, we can have a curve for their testing loss, the validation loss. The author wants to give us a summary for the pattern as the name is power law. Larger model can be better, can get better performance with more compute. By the way, do you believe this? So again, I think that we don't know. It's also just empirical study. We are not sure our model is converged or not. It's non-convex normalization. We don't know. Okay. Probably in the future we can get a different pattern. Yeah. So the empirical study results for GB3 is very good. Right? They can get very good results. You see here, a few shot is better than zero shot because the zero shot is a fake. Maybe we should trust few shot more. A few shots can get better results. And also the same pattern you see, a larger model we can have results. Okay, so today, so we know ChatGPT were successful, so here is GPT-3. So the next lecture we started GPT-4 InstructGPT. For GPT-3 still has many limitations. I think so fundamentally their objective function is not very good because they treat each token equally. Because maybe some tokens are more important than other tokens, not very. Maybe in the future we need a better function, better objective function. So again, the same issue in GPT-2. We just cannot confirm it's not AGI or it's AGI or not. Because we learn so much data, maybe many patterns we can just learn from the data. Maybe it's just a copycat. It's just a copycat. Yeah. So probably I heard a quote, so ChatGPT has a memory of the whole internet. So ChatGPT has a memory of the whole internet. Or ChatGPT is a compressed file of the whole internet. Yeah. So yeah, there are also some other issues of ChatGPT. Like as I mentioned in the video before lecture, it's safe or not bias. So it's very interesting. So you see, they tend to they have different limits for different rates. That's very dangerous for the future. Okay. Now let me give you more information about the cost of GPT model. So by the way, I want to share your data, the price per kWh, the price of the energy cost. US is roughly this number. So you see that's the cost for training the model. So even for the energy power, it's so high, we also needed to buy the hardware, right? Also, we needed to maintain the hardware for a long time. And how about today? We know we use Google every day, right? In the future, maybe we use ChatGPT every day, but every query of ChatGPT is 15 times more expensive than Google. That's the data you like, you can check. That's why today, even for OpenAI, they cannot make money because the service is too expensive. Every query they lose money. So we use more, they use more money. So yeah, so here is for a different model for the CO2 energy cost. You see, you want to make a comparison between here and that's a human energy cost by a human for 1 year. That's a car for the whole lifetime, like 15 years, or single way 10 years, like a car. That's a flight energy cost for a flight for per person from New York to San Francisco. You see the energy cost of training model is so high. So I believe that's a very important topic for the future. To build a clean AI to reduce the energy cost of energy efficient AI. Okay, now we are reaching to the end of this lecture. Let's do a 3-minute quiz. So as you know, that's the dimension for different GPT model. That's number of layers. That's structure for the attention. That's structure for the model. So can you compute the number of parameters for each model? Let's do just 3-minute quiz. Yeah, you need to know how to compute. Just try to write down or something. Yeah. Okay, anyone wants to share? Okay, I'm sorry, we don't have enough time. How about we just check the answer? So, you probably, the most important thing, you need to know how to compute it. Yeah. After you successfully finishing compute the non-parameter, you know the every details of the model. That's very important. So, firstly, that's attention, which is the key. Right? For attention, we know we needed to save the parameters. We have the QKB, right? WQ, WK, WB, and also the output we also have O here. That's their dimension. The model just dimension of the model. DQPB just dimension of QKB vector. They are the same. Also, we know we have this relationship. So DQKB is equal to DK, DQDB also equal to D model over N hat. Right? That's just how we made the transformer. So firstly, we need to compute the attention parameter in the attention. That's WO, right? WO. Because why we pass the demultiplied bias? We have bias term. Right? And also the same idea for QPV. Number has also QPV 3, right? Q1, T2, V3. We have three topics. Now we can just rewrite this part to this part. After rewriting this part is 4, just 4 times the part, right? It's roughly 4 times the model squared. Some parameter is the model. So the question here is why we can rewrite this part to this part? Because we use this relation, DQKB equals D model over N hat. Exactly, you can double check. Okay, so the number of parameters in attention is 4 times the model square. Any questions for this? And also the next part is the computer's feed-forward network, or the multi-layer perception. Different name, but same idea. So for here, we have assumption. So the dimension of feed-forward network is 4 times dimension of the model. That's just commonly used setting. So for feed-forward network, the first layer, right, we can just multiply that means bias. Also, that's the second layer, that means bias. We just rewrite everything because the feed-forward 4 times the model. We rewrite everything to get this. That's a number of parameters in the feed-forward layer. And also, so I asked a question. So what's the input? The input shape of the layer norm is 10 billion by 2 million. What's the output shape? It's the same, right? It's because it's element-wise operation. You see here for each element I have two hyperparameters, right? In total, it's 2 times the model. Because the model is a very large number. You see here is roughly the model square. Here is also the model square. So this part is minor when computing the number of parameters. So now let me give you more information. The model for different GPT firstly is attention layer at 4 times d model square, and then number of parameters is the feed forward network. And we know we have different blocks for GPT-1, it's 12, GPT-2, 48, GPT-6, 96. In total, that's number of parameters. Here, a little different from we learned from the paper because we don't count the layers and of their norm and also embedded layers. Yeah, I think this is very important. Please make sure you can get the correct answer by your hand. Yeah, please do a practice after the class. If you didn't get the correct answer, this is probably the most important thing. You should be very technical, know the technical details. Yeah, again, this is important. Check data after class. So now, let me, because GPT is so important today, let me also briefly introduce the code. So let me just use an example of mini GPT. Sorry, my GPT. So it's minimum Python implementation for GPT. So some to our TA, we have our variant. Like you can check the TA's variant. Let me explain this particular variant, but TA has some comments to the code to make it easy to understand. Let me, so the key part of this code is model, define model, trainer, how can we train? Now, let me explain the code for you. Okay, so here is an implementation for the GPT. Yeah. So you see, probably you just wanted to make sure how many parts is code we have. Yeah. So you see, we now just have an overview of the code structure. So firstly, that's just you see this code only have 4 parts, right? That's the activation function, right? The new glue, they just write a new activation function. It's easy to understand. This part is also want to write as a self-attention, the attention by himself. That's the GPT block. That's the GPT model. The structure of the code, this code is very, I think, very elegant. Now, let's check this part first. So you see the author just want to write his own attention. But I feel like you can use the predefined attention. But I encourage you to rewrite this code because you know all the details of the attention. So firstly, that's a comparison. So QPV. So the author here, firstly, we just put the QPV together in a matrix, right? And then later we partition them. But here we just put them together in a matrix. And that's just output the projection. And then that just drop out, right? No, drop out. Okay. So this part is very important. This part, we wanted to make sure the attention only applies to the left of this sentence, right? Because it's next token prediction. What is code doing? So we just build a lower triangular matrix here. We build a lower triangular matrix. So block size is a maximum sequence length. So we just to make sure it's a triangular matrix. Only one part of the matrix is being used. Because we want to make sure the attention only to the left of the input sentence. Right. And then for the forward, and firstly we want to get the size. From here we have to get that size, sequence length, embedding dimension. Okay. And then is we do partition, because as I mentioned that they put everything in a matrix. Now we partition them into QKV. Now we do a matrix transpose to make the dimension to be number of head by T, number of contact lengths, and by the distance. So here it just reshapes to just do a matrix transpose. Now here is a Q key operation, right? It's a dot product, and so here is master view. So we set the element is 0 to minus infinity because later we use max. The minus infinity, max for minus infinity is 0. Right? And then it will pop. And then it's attention store and the value. And then just use dropout output. Then that's attention. You see, I think it's not too complicated. That's attention. Now we go to the next part. After we build our attention, now how about the building block for GPT? So you see the building block has layer norm, has attention to layer norm and multi-layer perception. Easy to understand. Right? So just to follow the path, so here it's different from the paper. They use the layer norm before the representation, right? So if you like, you can check the paper. So actually, layer norm after attention. So here is a little different, but that doesn't matter too much. It's just a GPT block. Okay. As I mentioned here. Yeah, the GPT block here. Okay. That's a key part of the GPT model. That's just the second part. Now we have the block. Now we just build the GPT model. So GPT model firstly is the settings, not very important. And now let's take a look at here. So firstly, it's initialization. So here, the author defined many different versions of GPT. Yeah, you can just pick one of that. And then transformer here is very interesting. They actually build a dictionary. By this, they can just use the key to query each part. That's a good implementation. You see, in this transformer, firstly is token embedding and position embedding. That's your power. So that's also a module list which has all the, yeah. So yeah, so it's just a list of controller. All the controller blocks are here in this module. Later you can just use this module is all the transformer blocks here, and then layer node. And then is a head. So in their code, they can just later print out the number of parameters. How can we compute the parameters? You can just go over the transformer. Yeah. Let's see. All the transformer blocks are here. You see, so by the way, so here I want to clarify. So the name here is transformer, but also it's part that they have the embedding to implicit embedding and the transformer of the other layers. And then is that's just initialization. We can also to use a pre-trained model. Okay. So yeah, so here are some more details that you like to check. How can we use a pre-trained? Yeah. So this part is also built their own optimizer, but it's just an atom with a decay. Why they want to build their own write his own optimizer? Because PyTorch has the NMW implementation. Because the author want to build a wide list, only the part in the wide list can use with decay. Because I think so some layers also want to use VDK, other layers also do not want to use VDK. That's also internal study. So you see here, so I think okay. So you see, only the layer in this list can use VDK. Not all the layers use VDK. Otherwise, it's just, for example, bars, no VDK, right? Bars, no VDK. Or the layers in the white blacklist, no VDK. Right. So there are layer norm embedding bars, no VDK for that. And then is forward. I think it's very straightforward here. So we can just finish forward GPT. That's the topic embedding, that's a position embedding. So here, B is XIT, is a contact lens. So we can just go over each block and then compute the logics and then use a cross entropy to finish the computation. Now is check how can we generate this new token. So this part actually is a little interesting. So the author defined the temperature here, but the default setting temperature is just 1. It doesn't matter if it's 1. So we want to use the temperature to control the accuracy of the model. For example, this temperature is very large, so logics of different words will be very closer. That means the probability of predicting the next digits is different, right? So if the temperature is small, so we can more certain on the generator. we want to use temperature controls accuracy of for generating next token. And after that, we can just compute the soul max, and then yeah, that's how we and then we can just put the next word to the sentence and then go up. That's just a very good implementation for GPT. Let's also take a look at the trainer. So again, I think if you want to read the code, you first want to make sure how many parts. For the code only has one part. It's just a trainer, right? First A is a setting. See, the number of workers actually for the data loader are not important, and it's not important. That's the batch size, learning rate. That's the hyperparameter used in randomizer with decay 0.1, grading the normal clipping to make sure the elements in the gradient vectors are not too large, make the training stable. Firstly, just to do some initialization is not important. Let's call back just some implementation tricks. And now we just run the model. How about we just firstly load the data? Firstly, just load data inside our workers. So because the data set is too large, we want to do it in parallel. That's why it has a number of workers. Because we can do it in parallel, different samples independent to each other. And then we train the model. So here, firstly, we utilize the gradient. So that's the training part, just to do a minor step. Okay, yeah. We just finished the introduction of the code. So here TA also has a demo for us. If you like, I think you can run this demo. Very simple demo. Yeah, we just want to use the GPT to do the sorting. If you like, you can just run this demo. You see, that the training data, and just print out an example. That's the configuration. We just use a very tiny GPT nano. How about if you like, let's check a GPT nano. You see, GP Nano only has 3 layers. Number of heads is 3. It's a very tiny number. Embedded dimension 48. So here we use a very tiny model. About I feel like you can later play. You can change data to micro to try. So here is just GP Nano. You see, it has roughly 0.1 million parameters. So here I just learning rate maximum iterations, number of workers for data load are not important here. See, we train probably 2,000 iterations as the training loss. You see training loss, it go down, going down, going down. Yeah. Yeah, so here is the training final score, and so here is a demo. Input the sequence this as our prediction. You see, it's sorted, right? It has a track this routing. Yeah. I think the data set is too small, so the training testing final score is. Now, how about I just briefly change? How about just train 200 iteration? Let's check the difference. Now, you see, it's not 100%. To solve it already 100%. Yeah, I feel like you can just play this toy example. It's certainly very interesting. And now I change to 100 iteration to see the difference. Yeah, you see the accuracy now is even lower, but still it's correct. I feel like you can also change it to a different model to play this example. Yeah. So for here, I think for today's lecture is almost over. Two important things. Firstly, please make sure you know how to compute this. That's very important. As a homework. Yeah, but it's optional. But it's very important. Also, encourage you to check every details of this code. That's a very elegant code. Please make sure you can rewrite this code. Please, yeah, two important things. After class, we will do that. Yeah. Okay, that's it. Thank you.